The rock in your hand is screaming. Not literally, but if you know how to listen, it's telling you exactly how the world ends. Right now, paleontologists are finding fossils that shouldn't exist. Marine creatures in mountain peaks, tropical forests buried under Antarctic ice, coral reefs turned to stone in the middle of deserts. And hidden in these ancient remains is a code, a pattern that repeats over and over again across hundreds of millions of years. It's a pattern of collapse. And we're living through it right now. This isn't about dinosaurs. This is about something far more urgent. Because the fossils aren't just telling us what happened in the deep past, they're showing us our future. And the message is terrifying. Let's start with a mystery. In the summer of 1991, a geologist named Paul Wignall traveled to Greenland. He was hunting for rocks from the Permian period, roughly 252 million years old. What he found didn't make sense. The fossil record showed a thriving ecosystem, layer after layer of marine life preserved in limestone. Brachiopods, ancient relatives of clams, trilobites, those iconic armored sea creatures, coral reefs stretching for kilometers, and then, in a layer barely thicker than your thumb, everything vanished. 96% of all marine species, gone. Erased from existence in what geologists estimate was less than 60,000 years. 60,000 years sounds like a long time, but in geological terms it's a heartbeat. It's a catastrophe happening so fast that evolution couldn't keep up. This event has a name: the Permian Triassic Extinction. Scientists call it the Great Dying. It's the closest life on Earth has ever come to total annihilation. And here's the disturbing part: we're starting to understand what caused it. And the mechanism is uncomfortably familiar. The answer is written in the chemistry of the rocks themselves. When Wignall and other geologists analyzed the Permian Triassic boundary layer, they found something strange. Carbon isotopes were wildly out of balance. The ratio of carbon-12 to carbon-13 had shifted dramatically, a signature that appears when massive amounts of carbon dioxide flood into the atmosphere. But where did the carbon dioxide come from? The fossils point to Siberia. 252 million years ago, a series of volcanic eruptions began that would last for nearly 2 million years. But these weren't normal volcanoes. This was flood basalt volcanism on a scale that beggars imagination. Lava poured across an area larger than the continental United States. The basalt layers, still visible today in the Siberian traps, are in some places 3 kilometers thick. 3 kilometers of solidified lava. The eruptions released trillions of tons of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. The planet heated up, oceans acidified, and life suffocated. This leads us to the pattern. Because the Great Dying wasn't unique, it's happened before, and it will happen again. Go back further, 375 million years ago. The late Devonian extinction. Another mass die-off, this time triggered by a combination of volcanic activity, ocean anoxia, and rapid climate change. 75% of species vanished. The fossil record shows the same signature. Carbon isotope anomalies. Evidence of global warming. Acidified oceans jump forward. 201 million years ago. The Triassic-Jurassic extinction. Volcanic flood basalts in the Central Atlantic magmatic province. Carbon dioxide spike. Global warming. Ocean acidification. 76% of species extinct again. 66 million years ago. The Cretaceous-Paleogene extinction, the one that killed the dinosaurs. This time, the trigger was different, an asteroid impact. But the mechanism was similar. The impact released massive amounts of carbon into the atmosphere. Global temperatures swung wildly. Oceans acidified. 75% of species gone. Do you see the pattern? Every major extinction event in Earth's history is preceded by a rapid injection of carbon into the atmosphere. The source varies. Sometimes it's volcanoes, sometimes it's asteroids. Once, during the Permian, it was probably methane released from melting ocean floor sediments, triggered by the initial volcanic warming. But the result is always the same. The climate destabilizes, ecosystems collapse, life dies. And here's where it gets personal, because we're doing it again. Right now. Humanity is conducting a geological experiment on a scale that rivals the great extinction events of the past. We're injecting carbon dioxide into the atmosphere at rates that exceed even the Permian-Triassic boundary. Let me give you numbers. During the Great Dying, carbon dioxide levels rose by roughly 2,000 parts per million over tens of thousands of years. That's catastrophically fast in geological terms. Today, human activity is adding carbon dioxide at a rate 10 times faster than the fastest natural rates during the Permian extinction. 10 times faster. The fossils are screaming at us, and we need to listen. But here's the catch. The fossil record doesn't just show us catastrophe. It also shows us recovery. And that's where things get truly strange. After the Permian-Triassic extinction, Earth was a wasteland. The fossil record from the earliest Triassic period shows ecosystems so simplified they're barely recognizable. Instead of diverse coral reefs, there are microbial mats, primitive bacterial colonies that hadn't dominated the ocean since billions of years earlier. It's like the planet regressed, reverting to a more primitive state. But life didn't give up. Slowly, over millions of years, new species evolved to fill the empty niches. And some of these species were unlike anything that came before. The extinction created opportunities. With the old dominant species gone, evolutionary experiments that would have failed in a competitive environment suddenly had room to flourish. On land, this is where dinosaurs got their start. Before the Triassic-Jurassic extinction, dinosaurs were marginal players, overshadowed by other reptile groups. But when those groups died out, dinosaurs exploded into every available niche. Within 10 million years, they dominated terrestrial ecosystems from pole to pole. In the oceans, new predators emerged. Ichthyosaurs, dolphin-like reptiles that evolved from land-dwelling ancestors. Plesiosaurs, with their impossibly long necks and paddle-like limbs. These creatures filled the roles left empty by the Permian extinction, but they did it in entirely new ways. This is the fossil lesson we need to understand. Extinction creates innovation, but the process is neither quick nor kind. Recovery takes millions of years, and the world that emerges is fundamentally different from the one that was lost. Fast forward to the present day. Paleontologists are now studying modern ecosystems with the same tools they used to analyze ancient ones. And what they're finding is chilling. The patterns of decline we're seeing in coral reefs, rainforests, and ocean fisheries match the early stages of past extinction events. Coral reefs are particularly telling. The fossil record shows that reefs are excellent indicators of ecosystem health. They're complex, biodiverse structures that require stable conditions to thrive, and they're usually the first to collapse when environmental conditions deteriorate. In the Permian-Triassic extinction, coral reefs vanished completely. They didn't return for nearly 10 million years. Today, we're watching reefs die in real time. The Great Barrier Reef has lost half its coral cover since the 1990s. Caribbean reefs have declined by more than 80%. The process is accelerating, and the fossil record tells us that once reefs cross a certain threshold, recovery becomes impossible on human timescales. But it's not all doom and gloom. The fossils also show us something hopeful. Life is resilient. Even after the worst extinction events, biodiversity eventually rebounds. The question is, what does the recovery look like? And who survives to see it? Here's where paleontology becomes prediction. Scientists are using fossil data to model future ecosystems. They're asking questions like, which modern species have traits similar to extinction survivors from the past? What ecological roles will need to be filled in post-collapse ecosystems? And how long will recovery take? The answers are sobering. Species that survived past extinctions tended to have certain characteristics. They were generalists, able to eat a wide variety of foods. They had wide geographic ranges. They could tolerate environmental variability. Many were small-bodied, requiring fewer resources. Apply those criteria to modern species, and a picture emerges. Rats will probably do fine. Crows, jellyfish, cockroaches, of course. Meanwhile, specialists like giant pandas, polar bears, and most large predators are at extreme risk. They're the equivalents of the species that vanished in past extinctions. And humans? We're a paradox. On one hand, we're incredibly adaptable, capable of surviving in nearly every environment on Earth. On the other hand, our civilization depends on stable climate and functioning ecosystems. We've built a complex, interconnected global system that's proving remarkably fragile. The fossil record suggests that complex, specialized societies don't survive major environmental disruptions well. Simplification is the rule. Resilience requires flexibility, and flexibility often means abandoning complexity. This leads us to the final question. Can we break the pattern? Is it possible to avoid the fate written in the rocks? The fossils say yes, but only if we act with unprecedented speed and coordination. Every past extinction event was driven by runaway processes, feedback loops that accelerated once they started. Warming triggered methane release, which caused more warming. Ocean acidification killed calcifying organisms, which disrupted nutrient cycles, which caused more ecosystem collapse. But humans have something no other species has ever possessed: foresight. We can read the fossil record, we can see the warning signs, we can change course. The question is whether we will. Right now, we're standing at a branch point in geological history. Future paleontologists, whether human or something else entirely, will look back at the rocks forming today and ask what happened. Will they see the signature of another great extinction? Carbon isotopes swinging wildly, biodiversity plummeting, ecosystems simplified to bacterial mats and opportunistic survivors? Or will they see something unprecedented? Evidence of a species that saw the pattern and chose to break it. A thin layer in the rock record where carbon emissions peaked and then reversed, where biodiversity stabilized, where the trajectory changed. The fossils can't tell us which future we'll choose, but they can tell us what happens if we choose wrong. And that message is carved in stone, literally, in layers of rock spanning hundreds of millions of years. Every fossil is a time capsule, a message from a world that no longer exists. And right now, those messages are unanimous. They're telling us that the path we're on leads to collapse. Not might lead, will lead. The mechanism is well understood, the pattern is clear. But fossils also tell us that endings aren't final, that life finds ways to continue, to adapt, to rebuild. The planet will survive this. Life will survive this. The question is, what will survival look like? And who will be here to see it? Pick up a fossil. Hold it in your hand. You're touching deep time, holding evidence of worlds long dead. And in that ancient stone is written both a warning and a promise. The warning, what has happened before, will happen again. The promise, change is always possible. Evolution never stops, and the future is unwritten. The prehistoric echoes are getting louder. It's time we started listening.